Welcome, everyone. Take a moment and imagine the vastness of space, the stars, the galaxies, the endless darkness stretching out beyond what our eyes can see. Today, we are about to embark on a journey, not just across the stars, but into one of the most mysterious, mind-bending phenomena that the universe has ever presented us with: black holes. Now, maybe you've heard of black holes before. Maybe you've seen them dramatized in movies like Interstellar. Maybe you've read about them in science magazines or caught snippets of them in the news. But here's the thing. Even though black holes sound like something from science fiction, they are very real. And even more fascinating, they challenge everything we think we know about physics, reality, and even time itself. But I want to make something very clear right from the start. You don't need to be a physicist to understand what we're about to talk about. You don't need to know complicated equations or memorize scientific jargon. All you need is curiosity. The same curiosity that's driven humanity to look up at the night sky and wonder, what's out there? In this lecture, we're going to strip away the confusion. We're going to break down black holes step by step, slowly, clearly, so that anyone can follow. Whether you're a science enthusiast, a casual learner, or someone who simply wants to understand how the universe works, this is for you. And by the end, I guarantee, you will not only understand black holes, you'll see them as one of the most profound and awe-inspiring features of our cosmos. Before we even get to black holes, there's something important we need to understand. Black holes don't just appear out of nowhere. They're not random holes floating in space like traps. Black holes are the product of a cosmic story. A story of life, death, and transformation. But on a scale almost too big for the human mind to grasp. Think of the universe as a grand, ever-evolving stage. And on that stage, the most prominent players are stars. Stars of all shapes and sizes, from tiny red dwarfs that barely glow, to massive blue giants burning fiercely, living fast, and dying young. It's these stars, the heavyweights in particular, that play a crucial role in the formation of black holes. So, to truly appreciate what a black hole is and why it exists, we need to rewind the clock a little. We need to understand how stars live their lives, and more importantly, how they die. Because at the heart of every black hole lies the death of something colossal. Now, before we move forward, let me share why black holes captivate scientists and dreamers alike. They represent extremes: the strongest gravitational pull, the densest objects, the strangest effects on space and time. And here's the kicker: they are invisible. Literally invisible. They don't emit light, they swallow it. Imagine something so powerful, so heavy, that it can pull in entire stars, entire clouds of gas, even light itself. And once it crosses a certain boundary, it's gone. Forever. It sounds like magic, but it's not. It's the result of the laws of physics taken to their absolute limits. That's why scientists don't just study black holes to understand them. They study black holes to understand the universe itself. Gravity, space, time, even quantum mechanics. Because black holes sit right at the crossroads of everything we know, and everything we don't know. So, here's how this journey is going to unfold. We'll start by talking about stars, their life cycles, what keeps them alive and what causes them to die. Then we'll talk about how black holes form. What happens when a star collapses in on itself? We'll look at what's inside a black hole, or rather what we think is inside, because once something falls into a black hole, even our best tools can't see beyond a certain point. We'll explore how black holes affect their surroundings and how we've been able to detect them, even though they're invisible. We'll go deep into the strange and wonderful effects black holes have on space and time. And we'll end by asking some of the big, unanswered questions. What happens at the core of a black hole? Do black holes live forever? And what can they teach us about the future of the universe? So take a deep breath. Let your imagination stretch a little further than usual. Because over the next several sections, we're not just going to learn about black holes. We're going to confront some of the weirdest, most powerful, and most humbling truths about the universe itself. Ready? Let's begin. To understand black holes, we first need to understand stars, because black holes don't just appear out of nowhere, they are born from the death of stars. So let's take a step back and talk about what a star really is. What is a star? When we look up at the night sky, we see stars as tiny points of light, but in reality, stars are enormous. Take our sun, for example. It's an average-sized star, and yet over 1 million Earths could fit inside it. Stars are giant spheres of gas, mostly hydrogen and helium. They are born from massive clouds of gas and dust floating in space. These clouds are called nebulae. At some point, gravity begins to pull the gas and dust together. As the material collapses inward, the core heats up, hotter and hotter, until the conditions become just right. When the temperature and pressure at the center get high enough, a reaction begins. Hydrogen atoms start fusing into helium. This process is called nuclear fusion, and it is the secret behind a star's power. The balance of forces. Now, here's the beautiful part. Fusion releases an immense amount of energy. That energy pushes outward, trying to make the star expand. But gravity is still there, pulling everything inward. So the star settles into a kind of balance. Fusion pushes out, gravity pulls in. Push, pull, push, pull. This stable state is where stars spend most of their lives. This is called the main sequence stage. Our sun, for instance, is currently in this phase and has been for billions of years. But nothing lasts forever. Eventually, a star runs out of fuel. It begins to run low on hydrogen. When that happens, the core of the star starts to collapse. It gets denser, hotter, and for a time this causes the outer layers to expand. The star swells into a massive red giant, or supergiant, depending on its original size. But this is just a temporary phase. What happens next depends entirely on how massive the star is. Let's walk through the 3 main outcomes. 1. Low-mass stars, the white dwarf ending. If the star is similar in size to our sun, it will shed its outer layers. These glowing gases drift away into space, creating a beautiful planetary nebula. What's left behind is a tiny, dense core called a white dwarf. Imagine packing the mass of a star into something about the size of Earth. White dwarfs don't collapse any further. They slowly cool over billions of years like a fading ember. No black hole here. Just a quiet, dense relic of what was once a brilliant star. 2. Medium-mass stars. Neutron stars, and supernovae. Now, let's consider a star that's several times more massive than the Sun. When this kind of star runs out of fuel, it doesn't go gently. Its core collapses rapidly and the outer layers explode in a supernova. One of the most powerful and luminous events in the universe. A supernova can outshine an entire galaxy, even if just for a few weeks. What remains after the explosion is a neutron star. This is an object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are made almost entirely of, well, neutrons. They're just unimaginably compact balls of matter, often spinning rapidly and emitting beams of radiation. Still no black hole, but we're getting close. 3. Massive stars. The birth of a black hole. Now we come to the real heavyweights. If a star is more than about 20 to 30 times the mass of our sun, even a supernova can't save it from collapse. Gravity becomes unstoppable. There's no force strong enough to push back. The star's core collapses completely, endlessly, until it forms a point of infinite density, a singularity. This is the birth of a black hole. The outer layers may be blasted away in a violent explosion, but the core has already collapsed into something from which not even light can escape. Recap. Life paths of stars. So let's review the life paths of stars. Small stars become white dwarfs. Medium stars explode into supernovae and become neutron stars. But the most massive stars become black holes. Black holes are the ultimate consequence of gravity. They are what happens when matter collapses beyond any limit we know. It's like nature asking, what happens when we push everything to the extreme? And the answer is a black hole. The big picture. So why does this matter? Because when we see a black hole in the universe, we're not just looking at an object, we're looking at the remains of a star's life. A star that lived, burned, collapsed, and became something entirely new. A black hole isn't just destruction, it's transformation. It's the next chapter in the story of the cosmos. And now that we understand how black holes are born, we're ready to explore what they actually are. In the next section, we'll look closely at what makes a black hole tick, from the mysterious singularity to the boundary known as the event horizon. Let's continue our journey into the unknown. Now that we understand how black holes are born, from the dramatic death of massive stars, it's time to zoom in and ask the next big question. What is a black hole, really? What's inside one? What gives it its bizarre properties? And what happens at the very edge? Let's break down a black hole into its key parts. Believe it or not, we can describe a black hole's structure, even if we can't see it directly. Before we dive into the structure, let's remind ourselves of what a black hole actually does. At its core, a black hole is an object where gravity is so strong that nothing, not even light, can escape. That's not just a dramatic phrase, it's a statement about the limits of physics. In everyday life, you can escape gravity by using enough energy. For example, if you throw a ball upward, it slows down, stops, and falls back. But if you launched it fast enough, over 11 kilometers per second, it would escape Earth entirely. That's called the escape velocity. Now, imagine a place where the escape velocity is faster than the speed of light. Since light is the fastest thing in the universe, nothing can get out. That's a black hole. But what does that actually look like? Let's walk through the structure of a black hole, layer by layer. At the very center of a black hole lies the most mysterious point in the entire universe: the singularity. This is where all of the black hole's mass is concentrated, a point of infinite density. Let that sink in. Infinite density. All the matter that once made up a star, now compressed into a single point. In mathematics and physics, when something becomes infinite, it usually means we've reached a limit where our current theories break down. And that's exactly what happens here. The singularity isn't something we can visualize. It's not a tiny black dot floating inside the black hole. It's a concept that tells us this is where space-time, as we know it, ceases to make sense. What's actually happening at the singularity? We don't know. Our current physics, the theory of relativity, predicts it. But quantum mechanics, which governs the tiniest scales of nature, doesn't agree. So the singularity remains a mystery, a place where our best scientific ideas come apart. Now let's move outward, just a bit, to what we can understand, the event horizon. Think of the event horizon as the surface of the black hole. Not a solid surface, there's no wall or structure there, but a boundary. It's the invisible edge where the escape velocity equals the speed of light. Once anything crosses this line, whether it's a rock, a spaceship, or a beam of light, it's gone. There's no way to get back. That's why it's called the event horizon, because no events inside it can ever affect the outside world, not even in theory. To someone falling toward the black hole, they wouldn't feel anything special as they cross it. There's no bump, no flash of light, but from the outside, things look very different. We'll talk more about that in a later section. For now, remember this: the event horizon is the ultimate one-way door in the universe. So how big is this boundary? It depends on the mass of the black hole. There's a formula, called the Schwarzschild radius, that tells us the size of the event horizon. For a black hole the mass of our Sun, the Schwarzschild radius is just under 3 kilometers. So if you compress the Sun into a sphere only 3 kilometers wide, you'd get a black hole. For Earth, you'd have to compress the entire planet into the size of a marble. That's how intense the gravity needs to be, but black holes can be much larger. Supermassive black holes can have event horizons millions of kilometers wide, huge enough to fit the entire solar system inside. And yet, no matter how large they are, the rule remains the same. Beyond the event horizon, nothing escapes. One important thing to remember is this: a black hole is not an object in the traditional sense. It's a region of space where gravity dominates everything. There's no solid shell, no crust or surface. You wouldn't land on a black hole. Instead, you fall through curved space-time, deeper and deeper, faster and faster, until you reach the singularity, or more likely, get torn apart along the way. It's pure geometry, mass warping space, and that warping controlling motion. It's less like falling into a thing, and more like sliding down a slope that gets infinitely steep. Here's the ultimate mystery. Because no information can escape from beyond the event horizon, we have no way of knowing what's truly inside a black hole. All we can do is infer based on physics. Some scientists believe that the singularity may not be a point at all. Maybe it's a kind of bridge, a wormhole to another region of space. Or maybe it's something stranger still. Until we have a working theory that unites general relativity with quantum mechanics, the interior of a black hole will remain one of the greatest unsolved puzzles in science. In summary, let's recap what we've covered so far. At the center of a black hole is a singularity, a place where density becomes infinite and physics breaks down. Surrounding it is the event horizon, the invisible boundary beyond which nothing can return. The size of the event horizon depends on the mass of the black hole and is defined by something called the Schwarzschild radius. There's no solid surface, no core as we imagine in planets or stars, just space warped to its most extreme. And beyond the event horizon, we can't observe anything. It's completely sealed off from our universe. Black holes challenge everything we think we know. They aren't just strange, they're cosmic riddles. And they don't just sit quietly in space. They interact, they grow, they even affect entire galaxies. In the next section, we'll explore how we know black holes exist at all. Despite being invisible, we'll look at the clues they leave behind and the powerful tools scientists use to reveal the invisible. Let's continue. Now here's the real puzzle. Black holes are invisible. They don't give off light, they don't reflect light, and they don't have a surface we can point a telescope at. So how can we even know they exist? It's a bit like trying to prove that something is there, even though you can't see it, touch it, or shine a flashlight on it. But here's the thing. Black holes may be invisible, but they leave behind a trail of evidence, a fingerprint, through their interactions with the world around them. Let's explore the different ways scientists detect these cosmic ghosts. 1. Watching stars move around nothing. Imagine looking up at the night sky through a powerful telescope. You spot a group of stars near the center of a galaxy. But something's strange. One of the stars is orbiting something. It's moving rapidly, curving around what seems to be empty space. There's nothing visible at the center of its orbit. No star, no glowing object, no gas cloud. And yet, the star keeps circling that invisible point. It's being pulled in by something with immense gravity. That's the first big clue. In fact, this is exactly how we discovered the supermassive black hole at the center of our own galaxy. The Milky Way. Case study, Sagittarius A star. At the very heart of our galaxy, 26,000 light-years away, lies something called Sagittarius A star. Astronomers have been tracking the movement of stars near this region for decades, and what they found is astonishing. There are stars whipping around this point at incredible speeds, some moving at thousands of kilometers per second. One star, named S2, completes an orbit around this invisible point every 16 years, a blink of an eye on cosmic scales. Now, using simple physics, Newton's laws, orbital mechanics, we can calculate how massive the thing at the center must be. And the answer? Over 4 million times the mass of the Sun, all packed into a space smaller than our solar system. There's no star, no cluster, no gas cloud dense enough to explain that. The only explanation that fits all the evidence is a black hole. 2. Accretion disks and X-ray emissions. Okay, let's talk about something called an accretion disk. When matter falls toward a black hole, say gas from a nearby star, it doesn't just drop straight in. It spirals inward, forming a swirling disk around the black hole. This disk spins faster and faster as it gets closer to the event horizon, and as it spins, it heats up. A lot. Friction and gravitational forces cause the gas to reach millions of degrees. That's hot enough to emit powerful radiation, especially X-rays. So when we observe space in the X-ray spectrum, using telescopes like Chandra or XMM Newton, we can spot these glowing, high-energy disks. And often, right in the middle of that glow, is a completely dark, invisible center. That center? It's a black hole. So even though we can't see the black hole itself, we can see the violence around it, the chaos, the heat, the radiation of matter being shredded and pulled inward. It's a bit like watching a whirlpool. You can't see the center, but you know it's there because of how everything else is behaving. 3. Gravitational waves. Listening to the universe. Here's one of the most exciting breakthroughs in recent years. In 2015, scientists detected gravitational waves for the very first time. These are ripples in the fabric of space-time itself, predicted by Einstein over 100 years ago. But what caused these ripples? 2 black holes, orbiting each other, merging into one. Imagine 2 massive black holes locked in a death spiral, getting closer and closer, until they collide in a cataclysmic merger. This event sends out gravitational waves, tiny distortions in space-time that travel across the universe. And in 2015, using an instrument called LIGO, short for Laser Interferometer, Gravitational Wave Observatory, we detected those waves right here on Earth. It was like hearing the universe for the first time, a whole new way to observe the cosmos without using light at all. Since then, we've detected many more black hole mergers. Each one gives us more data, more insight, and more proof that black holes are not just theoretical, they're real, active players in the universe. 4. Imaging a black hole. Yes, really. You might be wondering, have we ever actually seen a black hole? And believe it or not, the answer is yes. In 2019, a team of scientists from around the world released the first ever image of a black hole. Not a drawing, not a simulation. An actual image. It was captured using the Event Horizon Telescope, a network of radio telescopes spread across the globe, working together as one giant observatory. The target was a black hole in the galaxy, M87, about 55 million light-years away. What they captured was stunning. A glowing, ring-shaped disk surrounding a dark center. That dark center is the black hole's shadow, its event horizon. The glowing ring is light being bent and twisted by the black hole's immense gravity. It was a milestone moment in astronomy. Proof not only that black holes exist, but that we can observe them, even if we can't see them directly. Summary: finding the invisible. So let's recap how we detect black holes. We observe the motion of stars orbiting invisible points, especially near the centers of galaxies. We look for intense X-rays and radiation from accretion disks, matter being swallowed alive. We detect gravitational waves, ripples caused by black hole collisions, and we've even captured images of black holes by watching how they bend light around them. Black holes may be invisible, but they are far from undetectable. They tug on stars, they heat up gas, they ripple space itself. In many ways, they reveal themselves through the disturbance they cause, like footprints left behind in the fabric of the cosmos. And once you start looking, you begin to realize they're everywhere. In the next section, we'll explore the different types of black holes, from tiny stellar remnants to monstrous supermassive beasts that live at the heart of galaxies. Let's keep going. At this point, we've learned what black holes are. We've talked about how they form, what they're made of, and how we detect them. Now let's go one step further. Not all black holes are the same. Just like stars come in all shapes and sizes, so do black holes. Some are small, short-lived, and born from a single dying star. Others are ancient giants, millions or even billions of times the mass of the Sun, lurking quietly at the centers of galaxies. So let's take a closer look at the main types of black holes we know of, or suspect might exist. We'll start small, and work our way up 1. Stellar mass black holes. These are the most common type of black hole that we know about. They form from the collapse of massive stars, just like we talked about earlier. When a star at least 20 to 30 times the mass of the Sun runs out of fuel, its core collapses under gravity, forming a stellar mass black hole. These black holes typically range from about 3 to 20 solar masses. That means they're 3 to 20 times heavier than our Sun, but packed into a space only a few kilometers across. Imagine taking something with the mass of the Sun and shrinking it down to the size of a city. That's a stellar black hole. There could be millions of them scattered across our galaxy. But many are completely dark and quiet, just drifting through space. We only detect them when they interact with something nearby, like stealing material from a companion star or merging with another black hole. 2. Intermediate mass. Black holes. Now, for a long time, there was a kind of mystery in the black hole world. We had small black holes, stellar mass ones, and we had gigantic ones, supermassive black holes. But what about the in-between? Are there black holes that are, say, hundreds or thousands of times the Sun's mass? The answer is maybe. These are called intermediate mass black holes. They're the missing link. Not as small as the ones formed from stars, but not as enormous as the ones that live in galaxy centers. We haven't found many clear examples yet, but evidence is starting to appear. In 2020, astronomers detected gravitational waves from the merger of two black holes, and the result was a black hole about 142 times the mass of the Sun. This was the first strong candidate for an intermediate mass black hole, and it opened the door to a new class of objects. Where do these come from? Possibly from the merger of multiple stellar black holes? Or from the direct collapse of huge gas clouds early in the universe's history? We still don't know for sure, but if we can find more of them, we may be able to solve one of the biggest questions in astronomy. How do supermassive black holes form? 3. Supermassive black holes. Now we reach the monsters. Supermassive black holes are truly mind-blowing in scale. They're found at the centers of galaxies, including our own Milky Way. And their masses? Not tens, not hundreds, but millions, or billions of times the mass of the Sun. Let's pause for a second. A black hole with the mass of 4 million suns sits quietly at the center of the Milky Way, Sagittarius A star. But that's actually on the small side. In other galaxies, we've found black holes over 10 billion times the mass of the Sun. And despite their size, they fit within a relatively small region of space. Because remember, black holes are dense. Some of these could easily swallow entire solar systems. Now, here's the big question. Where did they come from? Supermassive black holes are too big to have formed from just a single star. So how did they get so massive? There are a few theories. They may have started as smaller black holes and grew over billions of years by swallowing stars, gas, and other black holes. Or they might have formed very early in the universe, directly from huge clouds of collapsing matter. Or perhaps both. Some started large, others grew over time. One of the key goals of modern astronomy is to understand how these giants formed and how they shaped the galaxies around them. Because here's what we've learned. A supermassive black hole doesn't just sit at the center of a galaxy like a passive anchor. It influences the entire galaxy's formation and evolution. Its gravity can control star formation, influence the movement of matter, and even regulate the growth of the galaxy itself. In a way, galaxies and their black holes grow together. They evolve side by side. 4. Primordial black holes, hypothetical. Now let's step into the realm of theory. There's a fourth kind of black hole that hasn't been proven to exist. But if it does, it could solve some of the biggest mysteries in cosmology. They're called primordial black holes. The idea is this. In the first moments after the Big Bang, the universe was incredibly dense, hot, and chaotic. Tiny fluctuations in density may have caused certain regions to collapse into black holes. Well before stars or galaxies ever existed. These black holes would be small. Some could be the mass of a mountain, or even less, but they would still have the intense gravity we associate with black holes. If they exist, they might still be drifting through the universe today. Quiet, dark, and almost impossible to detect. Why does this matter? Because some scientists believe that primordial black holes could be part of the answer to another mystery. Dark matter, the invisible stuff that makes up most of the mass in the universe. We still don't know if primordial black holes exist, but they remain a fascinating possibility, and astronomers are actively looking for them. Summary: a black hole for every scale. So let's recap the types. Stellar mass black holes, formed from dying stars, a few times the mass of the Sun. Intermediate mass black holes, rare and mysterious, hundreds to thousands of solar masses. Supermassive black holes, millions or billions of solar masses at the centers of galaxies. Primordial black holes, theoretical black holes from the early universe. Maybe tiny, maybe key to dark matter. Black holes come in many sizes, but they all share one thing in common. They represent the most extreme expression of gravity in the cosmos. No matter how big or small, they challenge what we know about the universe and invite us to keep asking deeper questions. In the next section, we're going to get personal. What happens if you fall into a black hole? What would you experience? What would others see? Let's take a thought experiment and cross the event horizon. All right, let's shift gears. We've talked a lot about what black holes are, how they form, how we detect them, and how they're classified. Now let's get a little more personal. Let's imagine something wild. Let's imagine you fall into a black hole. What would that feel like? What would it look like from your perspective? And what would someone else watching you see? This might sound like science fiction, but it's a surprisingly serious question. One that physicists have actually spent a lot of time trying to answer. So let's go there. Let's take a one-way journey across the event horizon. The two perspectives, outside and inside. To understand what it's like to fall into a black hole, we have to talk about 2 points of view. Your perspective, the person actually falling in, and the observer, someone watching from a safe distance far away from the black hole. Here's where things get trippy, because what happens in these two perspectives is not the same. And that's not an illusion, it's actually how space-time behaves near a black hole. Let's start with the outside observer. From the outside, you freeze in time. Imagine your friend is floating safely in space, far away from the black hole. They're watching you fall in, and they're getting real-time data from your spacesuit. Maybe you're waving at them, sending them messages, even recording yourself. But as you get closer to the event horizon, remember, that's the boundary of the black hole, something strange happens. From your friend's point of view, you start to slow down. Your signals come in later and later. The light reflecting off you becomes redder and redder, shifting toward the infrared spectrum. This is due to something called gravitational redshift. Light is losing energy as it climbs out of the black hole's gravity. Eventually, your friend sees you freeze, right at the edge of the event horizon. You never actually appear to cross it. You just seem to hover there, frozen in time, fading away. Your final moments become infinitely stretched out in time. From their perspective, you've become a ghost, locked at the edge of oblivion. But remember, that's only from the outside. Now let's switch perspectives. From your perspective, you fall in. Fast from your point of view, the person actually falling into the black hole. Time feels totally normal. You don't notice any freezing. You don't feel yourself slowing down. In fact, as you fall in, things seem to speed up. Why? Because as you get closer to the event horizon, the gravitational pull gets stronger and stronger. You begin accelerating faster and faster toward the center. There's no warning, no sign that you've crossed the event horizon. No light show, no rumble, no barrier. One moment you're outside, the next you're in. And from here on out, there is no escape. You are now inside the black hole, and you are falling unstoppably toward the singularity, the center. Spaghettification. Yes, that's a real word. Now, let's talk about what happens to your body. And yes, it's about to get dark, literally and figuratively. Inside the black hole, the pull of gravity becomes incredibly uneven across your body. Let's say you fall in feet first. The gravitational pull on your feet is much stronger than on your head. Even though you're only a few feet tall, the difference in gravity is extreme. This difference creates a tidal force and it stretches you. Your body begins to elongate, your spine stretches, your bones stretch. Even your atoms are pulled apart. This process has a name, and it's actually used in real physics. It's called spaghettification, because quite literally you get stretched out into a long, thin, spaghetti-like strand. Eventually, you're torn apart on the molecular, then atomic, then subatomic level. What caused it? The insane gradient in gravity, the tidal forces, inside the black hole. Is there any way to survive? So, is it possible to survive falling into a black hole? Technically, if the black hole is supermassive, millions or billions of times the mass of the Sun, you might not feel much as you cross the event horizon. Why? Because the tidal forces are spread out more gradually. The event horizon is farther from the singularity, so gravity doesn't ramp up as quickly. You wouldn't be instantly shredded. You might float through the event horizon without even realizing it. But here's the catch. Once you're inside, the outcome is still the same. You're still falling toward the singularity, and there is no path out. You can't send a message back. You can't change your course, and physics, as we understand it, can't save you. So, what happens at the end? This is where science meets mystery. We think you'd reach the singularity in a finite amount of time, and at that point, you'd be crushed into a point of infinite density. But here's the thing, no one really knows what happens at the singularity. Our equations break down there. It's like hitting the edge of the map. Here be dragons. Some physicists believe quantum mechanics might somehow prevent the singularity from truly forming. Others suggest that you could be transported to a different universe, or another part of space-time entirely. There are even theories that falling into a black hole could create a new baby universe. These are speculative ideas, of course, but they highlight how little we truly know. At the edge of a black hole, science meets philosophy, and beyond the event horizon, we step into the unknown. In summary, so what would it be like to fall into a black hole? To an outside observer, it would look like you froze in time, fading slowly. To you, time would feel normal, but you'd fall faster and faster. Depending on the size of the black hole, you'd either be stretched instantly or drift deeper before being torn apart. And at the center, you'd meet the singularity, a place where the laws of physics no longer work. Black holes are not just death traps, they're windows into extreme physics and possibly into new realms of reality. And that brings us to another strange consequence of black holes, what they do to time itself. In the next section, we'll talk about one of the most fascinating effects of gravity, how time behaves near a black hole. It's not just science fiction, it's real, and it might just be a key to understanding the nature of time itself. Let's keep going. Black holes don't just bend space, they bend time itself. That might sound like something out of a science fiction movie, but it's a real effect. Predicted by Einstein, confirmed by experiments, and pushed to the absolute extreme near a black hole. In this section, we're going to explore what happens to time in and around a black hole. We'll talk about time dilation, how time flows differently depending on where you are, and how black holes might even act as natural time machines, though not the kind you're used to. Ready? Let's talk about gravity and time. Time, not what you think it is. Let's begin with a simple idea. Most of us think of time as a steady, constant flow. A second is a second, a minute is a minute. But Einstein showed us that this isn't actually true. Time is not absolute, it's relative, meaning it depends on how fast you're moving and how strong the gravitational field is around you. This concept is part of Einstein's theory of general relativity, and it's been tested many times. Here's a fun example. GPS satellites have to correct for time dilation. Because they're farther from Earth's gravity, time moves slightly faster for them than it does on the surface. If we didn't account for this, GPS systems would be off by several kilometers each day. That's not theory, that's real. And it works because time and gravity are connected. So, what happens to time near a black hole? Gravity slows time down. Here's the key idea. The stronger the gravity, the slower time moves. This means that if you were floating near a black hole, just outside the event horizon, and I was far away watching from a safe distance, time would pass more slowly for you than for me. Let's say you spend an hour orbiting near the event horizon. When you come back, you might find that years, decades, or even centuries have passed for everyone else. You've aged 1 hour, but the universe has moved on without you. This isn't science fiction, it's science fact. It's called gravitational time dilation, and the stronger the gravity, the more dramatic the effect. Near a small black hole, the time difference might be seconds or minutes. But near a supermassive black hole, like the one shown in Interstellar, the difference could be enormous. In the movie, 1 hour on a planet near the black hole equaled 7 years elsewhere. And surprisingly, that's actually plausible given the right conditions. The closer you get, the slower time flows. Now let's take it further. As you move closer to the event horizon of a black hole, time slows down more and more, from the perspective of someone far away. Remember our earlier example? To an outside observer, someone falling into a black hole appears to slow down, freeze, and never quite cross the event horizon. That's time dilation in action. From your point of view, time feels normal. But from the outside, your time appears to stretch out. In fact, from that observer's point of view, it would take an infinite amount of time for you to actually reach the singularity. And yet, from your perspective, the whole fall could take just seconds or minutes. This strange warping of time is one of the most extreme and mind-blowing effects of a black hole's gravity. Could black holes be time machines? All right, let's entertain a bold question. Could black holes be used to travel through time? The short answer is kind of, but only in one direction. Because of time dilation, black holes allow for a kind of one-way time travel into the future. Let's imagine a scenario. You orbit a black hole for a few hours, just outside the event horizon. You experience a normal passage of time. Maybe you eat lunch, you listen to music, then you fly back out. But when you return, you find that hundreds of years have passed outside. To everyone else, you've disappeared into the future. That's real. That's based on the laws of physics as we know them. But going backward in time, that's much trickier. There are theoretical ideas like wormholes or rotating black holes known as Kerr black holes that might allow for loops in time. But we don't have any observational evidence that this is possible. And there are plenty of problems with paradoxes and instability. So while black holes might help us travel forward in time, traveling backward remains in the realm of speculation. Time, gravity, and the edge of understanding. Black holes show us something profound. Time is not a simple ticking clock. It's woven into the very structure of the universe. And gravity, especially extreme gravity, warps it in powerful, strange ways. They force us to rethink time as something flexible, something shaped by the geometry of space, something relative, not universal. And the closer you get to the singularity of a black hole, the more twisted and uncertain time becomes. What happens to time inside the black hole? Does it still move forward? Does it stop? We don't know. That's one of the biggest mysteries in theoretical physics. And until we can combine general relativity with quantum mechanics, we won't have a full answer. In summary. So what did we learn? Time flows slower in stronger gravity. Near a black hole, time slows down dramatically. From the outside, someone falling in appears to freeze at the event horizon. From the inside, time seems to pass normally until you hit the singularity. Black holes may allow us to travel forward in time, but not backward. And ultimately, they challenge our very definition of what time is. Black holes don't just pull matter into darkness, they pull our understanding into unfamiliar territory. They show us that time, this thing we take for granted every day, is anything but simple. In the next section, we'll explore another mind-blowing idea. Are black holes forever? Do they just sit in the universe endlessly swallowing matter? Or can black holes die? Let's find out. We've covered a lot about black holes. How they're born, what they're made of, how they bend time, and more. But now it's time for another big question, and it's one that might surprise you. Do black holes live forever? They seem unstoppable. They swallow everything. They don't emit light. They don't let anything escape. So it's easy to imagine a black hole just sitting in space forever, growing larger as it devours matter, endlessly existing in the dark. But believe it or not, black holes can die. Not violently like the stars they come from, but slowly, invisibly, over immense stretches of time. And this discovery came from one of the most brilliant minds of the 20th century, Stephen Hawking. Let's dive in. The game changer? Hawking radiation. In the 1970s, Stephen Hawking asked a question no one else was really asking. What happens when we apply quantum mechanics to the edge of a black hole? Remember, black holes were understood as places where nothing escapes. Complete darkness, perfect absorbers. You throw something in, it's gone. But Hawking showed that when we consider the quantum nature of space, things get a lot weirder. According to quantum theory, even empty space isn't truly empty. It's a roiling sea of virtual particles. Tiny pairs of particles and antiparticles constantly appear and annihilate each other. This happens everywhere, even right next to the event horizon of a black hole. Now, here's where the magic happens. If a pair of particles appears right at the edge of the black hole, one might fall in, while the other escapes. The one that escapes carries energy away from the black hole. From a distance, it looks like the black hole is emitting particles. This process is called Hawking radiation, and it means that black holes aren't entirely black. Evaporation over time. So what happens if a black hole is slowly emitting radiation? It loses energy. And because energy and mass are interchangeable, thanks to Einstein's equation, E equals mc squared, losing energy means the black hole is losing mass. In other words, the black hole shrinks. Very, very slowly. The larger the black hole, the slower it radiates. A supermassive black hole could take trillions upon trillions of years to evaporate. But a small black hole? It would radiate faster, shrink faster, and eventually reach a point where it emits energy explosively and vanishes. That's right. Black holes can, in theory, evaporate completely. This was a revolutionary idea. It turned black holes from eternal objects into temporary ones. Hawking's discovery connected gravity, quantum mechanics, and thermodynamics in a way no one had done before. It opened a new chapter in physics. Black holes have temperature and entropy. Let's take it one step further. If black holes emit radiation, that means they have temperature. And if they have temperature, they also have entropy, a measure of disorder or information. This was shocking to physicists. For decades, black holes were thought to erase information. Whatever falls in, lost forever. But if black holes can radiate and shrink, then maybe that information isn't truly lost. This sparked what we now call the black hole information paradox, a major unsolved problem in theoretical physics. Does information that falls into a black hole really vanish? Or is it somehow encoded in the Hawking radiation as the black hole evaporates? We don't know. Physicists have proposed dozens of ideas, from holographic principles to firewall theories. But the truth is, this mystery still sits at the heart of modern physics. It touches on quantum gravity, string theory, and even the nature of reality itself. Do we have evidence of Hawking radiation? Now you might be wondering, have we actually seen Hawking radiation? Not yet. It's incredibly faint, especially for big black holes. The radiation is so subtle it's easily drowned out by cosmic background noise. But scientists are looking, some are even trying to simulate black hole-like conditions in lab experiments, using sound waves or light in special materials, to test the underlying physics. So while we haven't directly observed Hawking radiation yet, It remains one of the most widely accepted and exciting predictions in theoretical physics. So, how long do black holes last? Let's do some rough math. A black hole the mass of the Sun would take about 10 to the 67th years to evaporate. That's a 1 followed by 67 zeros. For comparison, the age of the universe right now is only about 13.8 billion years. That means black holes, especially big ones, stick around for a long, long time. In fact, when all the stars have died and all the galaxies have faded, black holes will be the last thing left in the universe. They are the slow-burning embers of cosmic evolution, and only after everything else is gone will black holes start to disappear. In summary, so do black holes live forever? The answer is no. Thanks to Stephen Hawking, we now know black holes can emit radiation through quantum effects. This radiation causes them to lose energy, and therefore mass. Over immense timescales, they can evaporate completely. This raises deep questions about what happens to the information inside a black hole. And it connects gravity, quantum physics, and thermodynamics in an extraordinary way. In the end, black holes aren't just cosmic death machines. They're more like cosmic puzzles, complex, evolving, and mysterious. They come into being, they interact, and eventually, they fade away. But while they're here, they shape the universe in profound ways. In our final section, we'll take a step back from the science and look at how black holes have entered our culture, our imagination, and our understanding of the universe at large. Let's wrap things up in Section 9. By now, you've taken a full journey through the science of black holes. From their violent births, to their invisible structure, to the way they bend space, time, and even logic. But black holes aren't just scientific concepts. They've become something more. They've entered our culture, our stories, our imagination. Few things in science have captured the public's attention quite like black holes have. They show up in movies, books, games, art, and even music. They've become the ultimate symbol of mystery, danger, and the unknown. Let's take a step back from the equations and event horizons and talk about what black holes mean to us. Black holes in movies and media. If you've seen any modern sci-fi film involving space, odds are there's a black hole in it somewhere. One of the most famous examples is the film Interstellar, released in 2014. In it, a team of astronauts travel through a wormhole near Saturn, only to find themselves near a massive black hole named Gargantua. What makes Interstellar special is this. The black hole wasn't just a Hollywood CGI creation, it was based on real physics. The filmmakers worked with physicist Kip Thorne, who helped simulate what a black hole would truly look like, how it would bend light, distort space, and appear to an outside observer. The result? A stunning, glowing ring of light around a pitch-black center, with the background stars warping and curling in impossible ways. That visual was so accurate, it actually led to a scientific paper. The movie inspired real astrophysical insight, and it brought black holes to the big screen in a way the public had never seen before. A symbol of the unknown beyond cinema, black holes show up in all kinds of stories. They're used as metaphors for the pull of obsession, the unknown parts of the human psyche, or the fear of crossing a line and never returning. You've probably heard someone say something like, "Be careful, that's a black hole of time," or "Don't fall into that mental black hole." They've become shorthand for something that draws you in, something overwhelming, something inescapable. In this way, black holes speak to something very human, our curiosity and our fear of the unknown. They represent the edge of understanding. And that's exactly what they are in science too. The first photo of a black hole. In 2019, the world was treated to a real-world history-making moment. Astronomers using the Event Horizon Telescope released the first ever image of a black hole. It wasn't science fiction, it wasn't a simulation, it was real. A glowing, lopsided ring of orange light, surrounding a dark, shadowy center. The black hole at the heart of the galaxy M87, over 50 million light-years away. that image became a cultural phenomenon. It was printed in newspapers, shared on social media, turned into posters, album covers, tattoos, even cakes. Why did it hit so hard? Because for the first time, we were no longer guessing. We were no longer imagining. We were seeing the invisible. That moment was a bridge between science and the human spirit. Proof that our species from our tiny blue planet could point telescopes at the sky, coordinate across the globe, and capture the silhouette of something that defies all understanding. Why black holes matter to everyone. So why do black holes resonate so deeply with us? Yes, they're scientifically fascinating. They teach us about gravity, space-time, and quantum physics. But more than that, they remind us of our place in the universe. They're bigger than us, older than us, and they operate on scales we can barely comprehend. But here's the beautiful part. We figured them out. With math, with logic, with imagination. Human beings made of atoms from old stars have decoded the secrets of these mysterious objects. And we did it not because we had to, but because we wanted to. Because we were curious. Black holes are a triumph of the human mind, and a reminder of how much more there is to learn. Looking ahead. We've come a long way. Black holes used to be a fringe idea, once dismissed as unrealistic or even absurd. Einstein himself wasn't sure they could exist, but today we observe them, we simulate them, we even listen to them through gravitational waves, and in the process, they're helping us piece together the biggest puzzle of all, how the universe works. We still don't know everything. We don't fully understand what happens inside a black hole. We don't know how to unite gravity and quantum mechanics. We don't know what happens to the information that falls in. But that's okay. Because the unknown isn't something to fear, it's an invitation. Black holes remind us that there's always more out there, more to see, more to understand, more to wonder about. And that's what science is all about. In our final chapter. So as we wrap up this journey, we'll take one last moment to reflect, to bring it all together. In the final section, we'll recap what we've learned, from stars to singularities to space-time and beyond. Let's finish strong. Ready for the final chapter? Let's close it out. We've come a long way. From the death of stars, to singularities that crush all matter and time, to the faint whisper of radiation slowly leaking out over trillions of years. We've traveled across light years of space and into the deepest wells of gravity. And now we reach the end of our journey, at least for now. Let's take a moment to pull all the threads together. What have we learned? We began with a simple question. What is a black hole? And we learned that a black hole is a region of space where gravity is so strong that not even light can escape. But to understand that, we had to understand how stars live and die. We learned how massive stars, at the end of their lives, collapse under their own weight. And if the conditions are right, they don't stop collapsing until they've formed a black hole. We explored the anatomy of a black hole, the singularity at the center, the event horizon around it, and the invisible nature of its structure. We discovered how black holes, despite being invisible, can be detected by watching stars orbit around them, by observing glowing accretion disks, by capturing their shadows, and even by listening to the gravitational waves they create. We explored the different types of black holes, stellar mass, supermassive, maybe even primordial ones formed in the early universe. We imagined what it would be like to fall into one, and discovered that time, space, and even your body behave in the strangest ways inside that dark abyss. We learned that black holes bend time itself, that time slows near the event horizon, and that the deeper you go, the stranger it becomes. Then we asked the big question, do black holes last forever? And thanks to Stephen Hawking, we learned that even these giants slowly lose energy, emitting radiation over vast timescales and eventually fading away. Finally, we stepped back and reflected on what black holes mean, not just to science, but to us, as symbols, as mysteries, as reminders of how far human curiosity can reach. What do black holes teach us? They teach us that the universe is still full of questions, that we've only just begun to understand the cosmos, that even the darkest parts of space can reveal the brightest insights. They show us how fragile and precious our understanding is, and how powerful our imagination can be. They push science to its edge, and they force us to ask deeper questions. What is time? What is space? What happens to information? What lies beyond what we can see? And perhaps most importantly, what comes next? Thank you. If you've made it this far, thank you. Thank you for spending this time exploring one of the most fascinating, humbling, and beautiful aspects of our universe. Whether you're new to astronomy or a seasoned space nerd, I hope you've learned something. I hope you've been inspired. And I hope you leave with more wonder than you came in with. Because the universe isn't done surprising us, not by a long shot, black holes are just the beginning. So keep looking up. Keep asking questions and never stop exploring. Until next time, stay curious and stay cosmic.